Hey gamers. Welcome to the last episode of the series. Last time we learned about the really cool Taylor series, which is how we approximate and know the shape of these really complex functions that we can't know on our own. And now, for the last video of the whole thing, we're just going to talk about some little extra applications and things you can do with Taylor series and power series. This should be simple and fun. The first, so with Taylor series, you've got that whole long process of finding the derivative, and then the second derivative, and then the third derivative to approximate this thing. And if you want greater accuracy, you can go on forever. But there are those simple series that we do know. We've got e to the x, sine of x, cosine of x, and there are some others that are easy enough to memorize. And what you can do with those is you can build more complex functions with those simpler functions. For example, oh, by the way, I'm using red today because our black marker died the other day. We know that e to the x is the simplest Taylor series of all. It's x to the n over n factorial. So simple, so pure. But what if we want e to the x squared? Or e to any function of x? What if we had something weird with x up there that we're raising e to? Well, I mean, it's in parentheses. Like, it's still e to something. And we know what e to something is. E to something is something to the n over n factorial. So that we can do the same thing here. We can just substitute whatever's on the inside in here. So we can just say this is x squared to the n over n factorial. And if we wanted to do a little simplification, this is x to the 2n over n factorial. And so you can just substitute in the things that make these like little changes to these simple series work. You can do the same thing with, for example, like if f of x is sine of 2x plus 5, well, we can't really represent that as a power series right now. But what we can do is we can represent sine of x as a Taylor series. We don't really know about sine of 2x, but it's on the inside. Like, this is still sine of something. And so we can just plug that something into our sine equation. We know that sine of x equals the sum of -1 to the n times x to the 2n plus 1, the odd alternating terms. And so, if we want to do a little change and say sine of 2x, you just shove it in there. Shove it in there. And then if you wanted to, you could substitute this out. But that's what sine of 2x is. There's probably a little bit of simplification you can do. And then, if you want to say plus 5, I mean, it's just a constant. You can add it on the end. So you can say, just like put it on the end of both sides. And so if you're going to write like the first 3 terms of the series that represents this, it would be, you'd start at 0. X to the first, so it's going to be 2x over 1. Or so you'll add your 5. First term will be 2x. Second term will be negative, what is that? N is 1, so that's 2x cubed, so that's 8x over, what's that? 3 factorial, 8/6 x, and then continues on. And you can write out the series like this for this thing that we don't necessarily know, but we know a simpler version of it that we can plug right on in. So that's Pretty simple. With Taylor series like these, if you see that it's in a form of something that we know, e to the x, sine of x, or even something that looks like a geometric series with that a over 1 minus r, you can make it into a power series just through substitution. So that's pretty interesting. That's pretty simple. That's pretty cool. Another thing you can do with these Taylor series is calculus-y stuff. We did a little bit of algebra-y stuff with substitution. You can also do calculus-y stuff with differentiation and integration. Say, for example, I've got like f of x is the sum of x to the n over n to the fifth. Now that looks kind of like something simple, but it's not. There's that n to the fifth. Oh, I dropped the marker cap, but I don't need it because I'm writing. So they'd give you this, and they'd say, hey, what is f prime of x? Well, even though this is in this scary, funky series form, like this looks like its own wacky thing, it's not. Remember, that summation notation is just a list of plus signs. This is just a ton of addition. This is just, what is it? When n is 0, it's just 1. Well, it's actually 0, so we're starting at 1. When n is 1, it's x over 1 plus x squared over like 32 plus dot, 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 right? It's just a list of plus signs. And what can you do with derivatives? Well, derivatives are distributive. I think that's a fun rhyme. Derivatives are distributive. So right, you can just say, like, the derivative of this is the same as d over dx of x plus d over dx of x squared over 32, dot, dot, dot. You can distribute the derivative to each term, which means that we can also just derive the general term. So we can take this general term and just stick our derivative inside of that summation. So we can just say d over dx, x to the n over n to the fifth. Because it's just a ton of plus signs. We're distributing it to the general term. However, it still might look like you can't differentiate that. Like you don't really know what's going on here. There's a lot of variables and there's a lot of ways that they're interacting with each other. But is there? Is there really? Remember, when we're distributing it to all of the inner terms, those n's aren't variables anymore. That n is a counting variable, which means that each term, in each individual term of this series, n is a constant, right? Like we had there with x squared over 32, n is just 2. And we'd know how to derive this if n was 2. And we know how to derive this if n is 3 and 4 and 5, etc. And so you can treat n in your derivative as if it were a constant. And this becomes really easy when this is a constant, because now you can just use the power rule. You don't have to use the quotient rule or the other one where it's multiplying with the opposite. You don't have to do anything like that. You can just use the power rule. Pull down that n, make it an n minus 1. When you've pulled down an n over n to the fifth is n to the fourth. And so this is just f prime of x equals a very lopsided summation sign, x to the n minus 1 over n to the fourth. That's all. You can derive each term and treat n as a constant. Super simple. You can do the same with integration. What if we had f prime of x equals n plus 1 times x to the n? Now, you can take the integral, and again, like derivatives, integrals are distributive. It doesn't rhyme as well, but integrals are distributive, so you can just take the sum of the integral. And luckily, I've made this very easy for us when we do the anti-power rule. Since it's dx, again, you can just treat these n's as constants. When you do the anti-power rule, you're increasing the step and then dividing by n plus 1. So you're saying f of x equals the sum of the n plus 1 divided by n plus 1 goes away, x to the n plus 1. That's all. Integrals and derivatives within the summation. It's easy. So that's really cool. Any power series, you can derive each individual term to get the derivative of the whole. You can integrate each individual term to get the derivative of the whole, or the integral of the whole. And you can also substitute into each individual term to get like a substitution of the whole. Perfect. So we've done a little bit of stuff to be able to deal with funkier series or do some funkier stuff to series. But now we're going to talk about like something that's very important for Taylor series themselves. And I've left this as the last thing because sometimes this is difficult. But I think it is easy to understand if you look past all of the scary number notation. When we have a Taylor series approximation, remember, it's always approximation. Because these series, right, when it's a series, it's infinite. And we can't calculate that infinity without a little bit of guessing. Yeah? And so generally, when you're actually using a Taylor approximation, it's just going to be a Taylor polynomial. It's going to have a finite number of terms. Like e to the x does equal the sum of, as n approaches infinity, of x to the n over n factorial. But that is still something that we can't like directly calculate, but we can approximate. We can say that e to the x is approximately, and then you list out terms in the series, like 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 32. And if we put the dot, 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 insisting that it goes on forever, then it's exact. But if we stop right there and have it just have these 5 terms, have it just be, this would be what they call a 4th degree Taylor polynomial, because the highest degree is x to the 4th, or the highest like n value, I suppose, is the 4. So with this 4th degree Taylor polynomial, how do we know how close we are to an actual value? Because an approximation is only really useful if you know it's any good. And so it's really important to know when we have good approximations, or how close our approximations are, so we're not making errors when we calculate things like e to the x or sine of x. And so I'm going to walk you through a way to find our error bound, like we did with alternating series. We can't find exactly how much we're off by, because that would involve knowing what the actual value is. But we can find the greatest thing we could be off by. We can find the bounds of our error, and we can know that we're closer than some arbitrary amount. Let's look at, I think I can erase this e to the x, some random wibbly graph. Oh man, the red is kind of dying on me too. It's okay, this is the last thing. If we look at some random wibbly wobbly graph, and let's say we want an approximation centered there. All right, so the first step, if we had a 0th term Taylor polynomial, that's just the constant. And the constant is a line that goes like that. Getting the marker cap. Now that's a pretty bad approximation, don't you think? I mean, it's right there, and it happens to also be right over there, but it's like still a bad approximation anywhere else. And so we make it a 1st degree Taylor polynomial, and that adds the slope. I'm going to make it green now. And you see, now that's a much better approximation, but still only very locally. And it's still pretty wild guess. It's not very close. And so then you'd add the rate of change of the slope, the curvature, if you will. You'll add the second derivative, making this a second degree Taylor polynomial. And so maybe another color. Maybe I've got brown. I didn't want to use brown, but I guess I'll use brown. You'll add the slope, and that will make it actually quite close. That will make it a parabola like that. And you see how this is getting a lot closer right near the point. But then, here, let's say maybe it gets farther and farther away from our function as our original thing becomes less like a parabola. But you see that with every successive term, we're adding to this Taylor series. With every successive power of the Taylor series, from a 0th degree to a 1st degree to a 2nd degree Taylor polynomial, we are getting closer and closer to the right value. Like if we're looking specifically, if we want to know what this series is right here. So if it's centered over here, and we want to know what is f of 1/2. Let's say this is 1/2, and this is f of x. Ignore that I'm using green and I labeled a red thing. We'd see that our 0th degree Taylor polynomial is pretty bad. And I think this is just a poor drawing, because if this were a little more accurate like that, our 1st degree is still really bad, but it's a good bit closer than our 1st degree. And then our 2nd degree is a good lot closer. And then our 3rd degree is going to push that approximation closer and closer and closer and closer. And so, by adding the next term, we're always getting closer to what our value is. And so, like we saw with the alternating series error bound, which was similar, remember when we drew out the sum of an alternating series, right? Like if this line is what the sum eventually converges on, it went something like this, where each time it got closer and closer to the sum. And we were able to use that to say that the next term probably overshot the sum. Now here we can't say that the next term overshoots the sum, because what if you had, I'm going to make a new little model because this one gets messy. What if you've got a function and a Taylor polynomial, and then the next term doesn't overshoot it, but it pulls it closer? Right? Like the difference from here to there pulls it closer, but it doesn't overshoot. So we can't say the same thing we did with our alternating series error bound, but we can use a similar principle. We can say the next term is probably very, very important. Now we get into some mathy stuff that you're just going to have to take my word for, because there's no simple proof of. This is very complex to prove. But Taylor, the guy who came up with these series, wanted to know how close he was. So he said that there is always a way for your Taylor series up to this point, like your partial sum. So let's call this S sub n, our Taylor series, plus the, oh no, I smudged it all bad, the n plus 1th derivative of x at some point over n plus 1 factorial over x minus c to the n plus 1. Okay, so I've just written a lot of math on the board. Sorry about that. The camera died. What I was saying is I just wrote, I'm not going to stand in front of it, I just wrote a lot of scary math on the board. But it's scary and complex in a way that hopefully you recognize. Because this, the scary and complex part, is just the general term of a Taylor polynomial, right? It's the nth derivative, but in this case it's the n plus 1th, divided by n plus 1 factorial times our little power series bit. But n plus 1 means it's the next term. So Taylor's theorem said that f of x equals our partial sum, or you could call this t sub n of x, the nth power Taylor, nth degree Taylor polynomial for x, plus the next term of it can equal f of x. But now you're going to be like, hold on. How come adding the next term now makes it equal? Because we just talked about how the next term can bring it closer, but won't ever make it equal, because you need infinite terms to make it equal. Taylor said that there is one important difference. If you plug in some different value z, not x, plug in some value z into this n plus 1th derivative of our next term, then it will be exactly correct. And importantly, he said that this number has to be between x and c. So Taylor argued that if you plug in some number between x and c, so between our center and the value we're looking for, there is some place where this next term will make it exactly equal. And that makes some sense, because if we're not doing this at x, this is basically just adding some constant to make something that's a little bit off equal. And now that's really helpful, because it tells us that we've got like this range of this much stuff, like from the place we're looking at to our center. That's the range of like where our possible values for this could come from, but it's not very helpful in that we can't ever find that, because that would involve knowing how much we're off by. But what it does is it gives us a jumping off point to find the maximum that we could possibly be off. Because a derivative or a function is often something that we can find the maximum of. And especially if they've given us this tiny boundary to look at, you can say that while we will never know when this is equal, we can say that, let's like subtract this to this side, and so we'd say the absolute value of our difference, again, just like in the alternating series error bound, the real sum minus our partial sum, so the real function minus our Taylor polynomial, our nth term Taylor polynomial, is less than or equal to the maximum of our next term. And this makes sense. Again, if we think about how every single time this is moving us closer, right? Like you're never going to get a next term of a Taylor polynomial. You're never going to add a new term and see this line not get a little bit closer if it's relatively close to the center, right? You're going to see this go from there to 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 there until it's very, very close to the line that we're approximating. And so if you're like, well, since this is getting me closer every time, the maximum of what could possibly get me closer, the maximum of our next term, the biggest our next term could possibly be, is probably, the line is probably within that range. Because like getting closer involves, let's do this a little bit cleaner. If we've got our Taylor polynomial, or like some degree of our Taylor polynomial, and it's there, there is this much room to get closer. So like if our next degree is there, the maximum it could possibly be and still get us closer, because it has to get us closer, we know that the real value is somewhere closer to us than the maximum of what our next term could possibly be. So the biggest change will probably, and by Taylor's theorem, it proves, actually, yes, the biggest our next term will be, the biggest our next term could possibly be, is greater than what we need to get to the sum. So like, this next term here is the error bound. It is the most we could possibly be off by. We know that we are closer than the maximum of our next term. And importantly, it's the maximum on a range. It's not the maximum of this derivative on its entire domain. It's the maximum on x to c. Not the drug, the range, x to c. The biggest that it could possibly be on this little range between our x and our center is our error bound. It's the farthest we could possibly be off. We know we are closer than that. And I know that still sounds like a lot, and it doesn't have to necessarily make sense. But if you know that you take the form of our next term for our Taylor series, the Lagrange error bound. This is called the Lagrange error bound because the error bound part was discovered or invented by a guy named Lagrange. The Lagrange error bound of our Taylor series at some place, so like some number of terms, if this was the fourth term, you'd look at the fifth term of our Taylor polynomial, take the maximum of this derivative, right? Because like you can take the maximum of this whole thing, but since these are all constants once we've plugged in a value, it doesn't matter anywhere but here. It's only this, this next derivative that we care about finding the maximum of, because the rest of these are essentially constants. You find the maximum of this next derivative on this range, and you've got your answer. And now sometimes, this is sometimes still hard to do, because we don't always know the n+1th derivative of this funky function. But often, at least on AP tests, they'll tell you something like, this function is decreasing. And so you'll say, well, so if it's decreasing and x comes before c, then x must be the maximum of this function. So you'd take f, the n+1th derivative of f at x, because you know that that's where the biggest value on this range must be. Or they'll give you a graph. They'll say the n+1th derivative. They'll say here's a graph of f, the n+1th derivative of f of x on our range. Here's from x to c. And it goes like, whoop. And you say, oh, there's the maximum. You plug that into here, and you say that our Taylor series must be closer than this value, than our Lagrange error bound, to the real value. So that's kind of a lot. And it may take a while of thinking about it and a while of doing practice problems to actually be able to use it. But once you can say however close you are to a real answer. So if I asked you to calculate e cubed without a calculator, you could do that. You could say e cubed you could say e cubed is 1 plus, and this is x, so this is 3 plus 3 squared over 2 plus 3 cubed over 6. And you could say, well, it's approximately this. And I could ask you, how close is it? And you'd say, well, it is at least, it is closer than the maximum of the nth derivative of e to the x is still e to the x. So we'd write this. The max of e to the x on, so from the center of this is 0, from 0 to 3, because that's where our x value is, divided by, we've gone up to 3, so our next term is 4 factorial, which is 24, times our x is 3 minus our center is 0, raised to the 4th. And we know that e to the x is an increasing function. And so the maximum of this is e cubed. And now that's actually super useless, because we don't know what e cubed is. But assume, for some function that you're doing this for, that as you derive it, you're given something, or you know something about its derivative, where you know the value of this maximum. So this will become some value. And then you could say that I know that this thing, this Taylor series that I've come up with, which is t sub 3 of x, is at least this close to our real answer. And I think that's really cool. It's the only reason that Taylor series are useful, because we can know how close our approximations are. And it'll come up once or twice on the AP test, which is the only time that you'll actually have to like plug values into this. But I think that's all I have for you. Thank you for coming on this little series journey with me. Thanks for putting up with the stuff that I say that is wrong. And thank you for watching. Sequences in series make sense, actually, sometimes.